Hey everybody, back for day number 7 of trigonometry. This is going to be a two-part lesson. In this part of the lesson, we're going to talk about inverse trig functions and do a little bit with solving. In part 2, we're going to talk, law of sines, law of cosines, as well as areas of triangles and sectors and segments and all that good stuff. So let's go ahead and get started with today's part 1 lesson. Okay, so I'm going to go ahead and get started here talking about sine and inverse sine. So first let's talk some basics. The sine function, its input, in this case A, is going to be an angle, and its output B will be a ratio. All right, so the input into sine is an angle. It's not an L, it's an angle symbol, and the output is a ratio. Now, when we talk inverse, on the other side, A, our input is now a ratio, and our output is an angle. So anytime you're working with inverse sine, or inverse cosine or inverse tangent, your output should be an angle measure. Okay, so let's graph a part of the sine function, and then we'll graph the principal portion of the inverse sine function. So I'm going to graph, ignore the values on the graph. This is not going to be to scale based on the labeling. But let's say that I have a portion of the sine function, right? And this would be a 1, and this would be a -1. And over here and over here, I would go from pi to -pi. Okay, so when we talk about inverses, an inverse is a function if and only if the original passes the horizontal line test, which this does not. So mathematicians decided, okay, let's restrict the sine function such that it would pass the horizontal line test. So its inverse would be a function. So these 2 points are the points -pi over 2, -1, and this would be the point pi over 2, 1. And of course, we've got 0, 0 here. So when we go from a function to its inverse, let me just sketch that portion of the graph that now we're looking at, which passes the horizontal line test. When we sketch its inverse, we flip-flop the domains and ranges. So let's first talk about the domain and range of sine of x. Okay, so the domain of sine of x, well, in all actuality, it's not limited at all to any value, so that'd be all real numbers. And the range of sine of x is limited to outputs from -1 to 1. As we know with inverses, the domains and ranges switch. Now, because we don't want the range of inverse sine to be all real numbers, because then it wouldn't pass the vertical line test, we restrict it. Okay, so let's sketch the red portion of sine plotted on the inverse sine graph here. Okay, so we're going to take each of these points, these 3 points in red here, we're going to flip-flop them, right? We're going to flip the x value and the y value. So the inverse sine will still take on the point 0, 0. Okay, but now it'll take on the point 1 pi over 2. Okay, so over 1 up pi over 2 units. So this would be the point pi over 2, 1 pi over 2. Okay, and then the point -pi over 2 comma -1 will become -1 pi over 2. Okay, so at this point then the inverse sine function comes to be sketched like that. Now, of course, we have restricted it so that we wouldn't have issues with the vertical line test. If we did, there'd be a problem there if we continued the function on in both directions, up and down. Okay, so let's talk domain and range of inverse. So the domain of of the inverse is going to be the same as the range of sine x, which is -1 to 1. The range of the inverse isn't going to be all real numbers because that would create a problem. It would no longer be a function. Therefore, it's going to go from -pi/2 to pi/2. Okay, so there we have inverse sine. Okay, inverse cosine, very similar. Okay, let's sketch a part of the cosine function. Talk about restrictions here. Okay, not my best sketch, but that's okay. This is the point 0, 1. This is the point pi/2, 0. This is the point -pi/2, 0. And these 2 points, this would be pi -1, pi -1, and pi -1. So similar restriction used. Whatever mathematician chose to do this, I don't know, I should probably do a history check. Restricted cosine from 0 to pi. So cosine's normal domain, of course, is all real numbers. And its range is the same as sine's range, -1 to 1. Now what we do then, of course, for inverse is its domain and range will be the domain and range of the other. So the domain of the inverse should be the range of the original, since they're inverses. But the range won't be all real numbers. The range will actually be the same as the domain of the restriction. And the domain of the restriction we've said is 0 to pi. Okay, so as I sketch these points out, what you'll see is I'm going to have the point 1, 0 instead of 0, 1. I'm going to have point 0 pi/2 instead of pi/2, 0. And then I'm going to have a point -1 pi. So -1 pi should be right about there. All right, so the cosine function, or inverse cosine function, should look kind of like that. Not well sketched, but that's what inverse cosine would look like if it were restricted. Of course, like we said, if we were to continue the pattern, then it wouldn't pass the vertical line test. We would have issues. Okay, arctan. Now notice that I haven't used this arc notation yet. It's equivalent to inverse, so this is equivalent to tan inverse of A equals B. Okay, and the tangent, this one's really easy to work with. It has natural restrictions at x equals -pi/2 and pi/2. Those are vertical asymptotes. The tangent doesn't exist there. Tangent hits specifically 3 points that are kind of easy to work with. The point 0, 0, so the tangent is 0, 0. -pi/4, -1, so the tangent of -pi/4 is -1. And pi/4, 1. Now when I take that and I flip it on its side, those vertical asymptotes become horizontal asymptotes. So I get y equals pi/2 and y equals -pi/2 as horizontal asymptotes. The graph of arctangent looks kind of like this, where this point is 0, 0. This point should be then 1, pi/4, and this point is -1, pi/4, excuse me. Okay, now just as we move into things here, anytime you're working with arcsine or arctangent, right? Inverse sine of x and inverse tangent of x. So notice the domain here, there's a bunch of discontinuities in the domain of tangent, right? But if I look at it simply on this restricted space, we would go from -pi/2 to pi/2. Okay, and its range is all real numbers. So as I look at inverse tangent, its domain actually is all real numbers, and its range is negative pi over 2 to pi over 2. But what we'll notice about sine, inverse sine and inverse tangent is that both have a domain, a range that lands in those quadrants 1 and 4, whereas inverse cosine, and this is just a visual that you can kind of work with when you think of where your answers would come from, right? So if I said, find the inverse cosine of square root of 3 over 2, right? The cosine is positive in two places, right? Here and here. So the cosine at this answer, technically speaking, you could say, well, hey, it's at pi over 6 and 11 pi over 6. 11 pi over 6, where this is pi over 6 and this is 11 pi over 6. Well, due to the restrictions that we put on inverse cosine, so that's a function, we're not going to utilize that. We're only going to utilize the one that falls in quadrants 1 or 2. So that's useful later on when we get to questions like that. So let's get into a couple of questions. We'll do a couple more solving questions, and then we'll move on to part 2. Okay, let's look at some inverse trig solving examples, okay? And your unit circle is very helpful to you. In some cases, it's not, and the answer won't be quite as pleasing, but in a lot of cases, it will be. So arctangent. So we just spoke about arctangent and how its solutions would be in quadrants 1 or 4. Well, the tangent, if it's negative, like this one is, should be in quadrant 4. So that's where we know our answer would be. Now, recall that in quadrant 4, though, the range of inverse tangent or arctangent goes from negative pi over 2 to pi over 2. So we need to make sure that the angle as our answer fits within those restrictions. So if I were to sketch in quadrant 4 a triangle, okay, where here's the angle that we're seeking. Clearly working with arctangent, our output will be an angle. So if I have a tangent of negative 1 over root 3, that would tell me the hypotenuse is 2, which means then that this angle x would have to equal negative 30 degrees or negative pi over 6. Okay, either of those two would be acceptable answers. If a question asks you in degrees or in radians, just make sure it fits. Okay, so there's our answer for number 1. Number 2, though, arc cosine. Well, cosine, we know, is going to fit in either quadrant 1 or 2. Well, the cosine is positive in quadrant 1, so I'm going to sketch my triangle in quadrant 1 with a cosine of 2/3. And here's x, again, looking for an angle. Okay, well, 9 minus 4 is 5, so the square root of 5 would have to be this value here. Now, this is not a unit circle friendly ratio that we're working with. Therefore, you would be required to use your calculator in this case. And I'm going to go with my calculator, which is currently in radian mode. And I'm going to take the inverse cosine of 2/3, and we're going to round this. Okay, using my calculator, using 3 sig figs, I get 0.841 radians. Okay, 0.841 radians. If you're working degrees, that would equal 48.2 degrees. Okay, all right, now let's look at number 3. Let's consider what we're looking for here. Inverse tangent of 4/7, that's an angle. So the sine of an angle should give us a ratio. So our output here, what we're getting out is a ratio. You could think of this as like theta, an angle. So if I were to sketch that angle, right, it's going to be in the first quadrant because it's a positive 4/7. And working with tangent, if it's positive, it's got to be in quadrant 1. So tangent is 4/7. That would make 49 and 16 is 65. So that would make this the square root of 65. So if I want the sine of theta, and I look at that diagram, the sine of theta would equal 4 over the square root of 65. Therefore, that's our answer. Or if you want to go a little bit further, if it asks you to put it in a different form, that would be 4 root 65 over 65. Outstanding. Let's look at number 4. Okay, here we go. We're starting to get into the meat and potatoes here. All right, so arc cosine, that's an angle. I'm going to call it theta. And arc cosine 1/2 is a different angle. I'm going to call that phi or phi, and not pho or phone. Notice cosine positive quadrant 1. So here is theta. Cosine is 3/5. That's a Pythagorean triple. I like that. And then phi also in quadrant 1. Cosine 1/2, 1 and 2. That would make this a root 3. So I already know that phi is going to be 60 degrees or pi over 3. Okay, based on nice unit circle friendly values. So I'm going to do the cosine of theta. This would be equal to the cosine of theta, cosine of phi, minus sine of theta, sine of phi. Now this is just using the compound identities we've already worked with. So anything that involves a theta, I'm going to use the red triangle. Anything that involves a phi, I'm going to use the blue triangle. So cosine of theta I already know is 3/5. Cosine of phi is 1/2. Sine of theta is 4/5. Sine of phi is root 3 over 2. All right, nice thing is we've already covered in this unit is that we will never have to find a common denominator. It'll just work out nicely for us. So this would be x. This is what x is going to equal, right? It's going to be a ratio because ultimately we're evaluating a cosine function. Okay, let's keep moving to number 5. All right, I got tangent of an angle. This is an angle. It's a double angle identity. So let's write the double angle tangent identity down. Tan 2 theta is 2 tan theta over 1 minus tan squared theta. In this case, what is theta? Theta is inverse sine of 3/5. So I'm going to sketch theta. Again, sine positive first quadrant. If the sine is 3/5, this is theta. That would, again, Pythagorean triple make a leg of 4 there. So the tangent of 2 theta, which is equal to x, should equal 2 times the tangent of theta. Well, the tangent of theta is 3/4. I get that directly from the image or the sketch. And then I'm going to then square 3/4 in the denominator and subtract it from 1. So let's do a little algebra here. That'd be 2 times 3/4. Did I do that right? Yes, I think I did. Yeah, I did. Okay, so 2 times 3/4 is 3/2. And 1 minus 3/4 squared is 9/16. Okay, so x equals 3/2 over 7/16. Okay, dividing by a fraction is the same as multiplying by a reciprocal, which would be 16/7. Therefore, we get a reduction. That would become an 8, so we would get x equals 24 over 7. So the tangent of 2 sine inverse of 3/5 ends up equaling 24/7. Okay, guys, I believe we're going to move on to some trig equation solving. So let's get it going. Okay, more with solving. The main reason I'm doing this is just because, well, we can always use more practice. Okay, so sine of 4x is equal to sine of 2x. I want to know where that's true. Well, I'm going to rewrite sine of 4x in its double angle form. So think of sine of 4x as sine of 2x's. It's kind of weird. But then imagine this is theta. All right, so sine of 2 theta, what's that? That's 2 sine theta and a cosine theta. But theta in this case was 2x. So I'm going to insert a 2x there for both of those. So sine of 4x is 2 sine 2x cosine 2x. And I'm going to subtract sine 2x over from the right side. And set the right side equal to 0. Now I'm going to factor out a sine 2x. That'll leave 2 cosine 2x minus 1 is equal to 0. Now using the zero product property, then sine of 2x should equal 0, or 2 cosine of 2x minus 1 should equal 0. That means, okay, so now this is where it gets interesting, right? Because we're going to double our solutions when we have the number of solutions when we have a 2 inside that function. So where does the sine equal 0? So let's see this. 2x is equal to the inverse sine of 0. Well, where is sine equal to 0? Sine is equal to 0 in quadrants 1 and 4 at 0 only. So that means 2x is equal to 0. Plus 2 pi k. Okay? So every 2 pi units, the sine is equal to 0. Actually, I should go even shorter than that. Plus pi k, right? Because at pi, the sine is 0 as well. We're going to utilize that in a minute here. Also, we would get that 2x is equal to the inverse cosine of 1/2. Okay, so the inverse cosine 1/2. Where is the cosine equal to positive 1/2? It would be in quadrants 1 and 4, right? So to some extent, the restriction is nullified here when we have double or triple angle. But let's just see what happens. Okay, so that means 2x is equal to pi over 3 plus 2 pi k. We could also say that 2x would equal 5 pi over 3 plus 2 pi k. So let's do that. Right, in quadrant 4. All right, so let's consider if 2x equals 0 plus pi k, then x equals 0 plus pi over 2k. All right, so that's going to yield a bunch of answers for us, right? We want to know all the answers where this is true. Well, 0, that's within 0 to 2 pi. So is if I put in a 1 for k, pi over 2. So is if I put in a 2 for k, that's pi. And 3 for k, that's 3 pi over 2. And I'm running out of room, gosh dang it. And as well as 2 pi. Okay, so that yielded for me 5 solutions. Okay, 5 solutions. Let's look at what these two would yield. Let's do this one in red. Okay, so 2x is equal to pi over 3 plus 2 pi k. All right, so that means x would equal pi over 6 plus pi k. So our first solution, if k is 0, is pi over 6. Our second solution would be 7 pi over 6. And our third solution, if I added 6 pi over 6, would be 13 pi over 6. But notice that 13 pi over 6 is no longer within the restriction from 0 to 2 pi. Okay, our last would be 2x is equal to 5 pi over 3 plus 2 pi k. All right, so that means x is 5 pi over 6 plus pi k. If I divided that by 2, I'd get pi k. So if k equals 0, I get 5 pi over 6. And if k equals 1, I get 11 pi over 6. Okay, so our solutions, you guys, are all 5 of these. The 2 here in red, pi over 6, 7 pi over 6, and the 2 in blue, 5 pi over 6 and 11 pi over 6. 9 solutions. It's pretty complicated there. Okay, let's look at the next one. All right, sine of x plus cosine of x equals root 2. In this case, there's no identity that's really going on here. So what I'm going to do is I'm going to square both sides. This is a strategy that can sometimes be used. In this case, we're going to, if I FOIL this left side, I get sine squared x plus 2 sine x cosine x plus cosine squared x is equal to 2. Now, sine squared plus cosine squared is equal to 1. So I would get, and actually this 2 sine cosine is sine 2x plus 1 is equal to 2. So that means that I can solve this relatively easily. I'm going to subtract 1 from both sides, and I get sine 2x is equal to 1. And then 2x then is equal to the inverse sine of 1. I want answers between 0 and 2 pi. So I'm going to take anywhere that the sine is 1. And the only place within 0 to 2 pi that's true is going to be, 2x would equal pi over 2 plus 2 pi k. All right, so then I divide by 2. That gives me pi over 4 plus pi k, and I'm going to go through the steps of 0, 1, and 2, and so on as far as I have to within the restrictions 0 to 2 pi. So that would be pi over 4 if k equals 0. That would equal 5 pi over 4 when k equals 1. I'm going to go out just another ways here, and 9 pi over 4 if k equals 2. Okay, so clearly 9 pi over 4 is greater than 2 pi, so that's out. So our solutions here are pi over 4 and 5 pi over 4. Outstanding. Let's look at number 3. Number 3, 2 sine x plus cosecant x. Well, that's weird. We haven't seen one with a cofunction like that. But a cofunction in this case is just 1 over sine x. So what I'm going to do across the board is multiply both sides by sine x. That'll get it in a form that'll be much easier to work with. So I'd get 2 sine squared x plus 1 is equal to 3 sine x. Now, one thing I have to be aware of is because of this cosecant, I cannot, if sine x equals 0, we would have a problem, right? Because we'd be dividing by 0, so we'd have a discontinuity. So if I get a pi over 2, or I get if any of my solutions that I need to be aware of, right? So where is sine x equal to 0? Well, it's equal to 0 when x equals 0 or pi or 2 pi or 3 pi, etc., right? If I get any one of those, it's an extraneous solution. We can't use it. So I'm going to work this through. 2 sine squared x. That'll be minus 3 sine x plus 1 equals 0. Let's factor that. That'd be 2 sine x and sine x. And I'm going to go minus 1 and minus 1. Okay, so as I solve this, this tells me that sine x equals a half. That means the inverse, x equals the inverse sine of 1/2. And then over here, this tells me that sine x equals 1, which means that x would equal the inverse sine of 1. Okay, so let's look for values between 0 and pi such that the sine is 1/2. Well, that happens in 2 places, right? The sine is positive in this entire interval from 0 to pi. Therefore, that would be at pi over 6 and 5 pi over 6. Neither of those show up in the solution set that we had as our values that would make extraneous solutions. But here, this would, right? So we would say x equals 0 and x equals pi. You might be fooled into thinking that. That's a problem. You can't use those because it would technically make cosecant undefined. Okay, I think we've got a couple more questions on the next page, and that'll be it for part 1. Okay, number 4. Tan to the 4th x plus 2 tan squared x minus 3. Now, this is kind of intimidating because it's tan to the 4th, but it's really not that bad. I can factor this as tan squared x and tan squared x. Right? Because you have this cascading to the 4th and to the 2nd, much like you would have, tan squared x plus 2 tan x. minus 3. You could factor that, but your leading or your terms would be tangent and tangent instead of tan squared and tan squared. So you can kind of see that nicely show up there for you. Okay, so we want the two numbers to multiply to negative 3 and add to 2, and it doesn't matter the order in which they go. So multiplying to negative 3 and adding to 2, that would be a positive 3 and a negative 1. Okay, we set that equal to 0. That means we want the tangent squared x to equal negative 3. In no way, shape, or form will that ever be possible, because you can't square something and get a negative number. So this will yield you no real solutions. As for our other expression, tangent squared x can equal 1. If I took the square root of both sides, that would mean we'd want the tangent to be plus or minus the square root of 1, which is 1. All right, so that means I'm kind of going to yield where would the tangent of x equal 1 and where would the tangent of x equal negative 1. Now within 0 to 2 pi, tangent, this is great. Anytime you get a ratio of 1 on tangents, tangent is positive here and here, and it's negative here and here. So pi over 4 or some factor of pi over 4 is where we get tangent equal to 1 or negative 1. So the negative outputs would be 3 pi over 4, or the inputs such that the output is negative 1 would be 3 pi over 4, and what would that be? 7 pi over 4, just short of 2 pi. Likewise, on the other side, the positives would be x equal pi over 4 and 5 pi over 4. Okay, let's look at one last question, and let's find all possible solutions here. So let's first start by dividing, make that a 3x by the 2 on the left side. So square root of 2 over 2 should tell you you're working with some form of pi over 4. Okay, now this is going to be quite interesting because we're looking for all possible solutions. So where would the sine, right? Where would the sine be a positive pi over 4, or root 2 over 2? Well, it would be here at pi over 4, right? That would be an output of root 2 over 2, as well as here in quadrant 2, where we'd have 3 pi over 4. So I'm going to yield two possible initial solutions. So that means that 3x is equal to pi over 4 plus 2 pi k, right? So this solution would repeat itself every 2 pi units. So we'd get 9 pi over 4, and then 17 pi over 4. I mean, I could write all these out. It would really be awful, but we could. As well as 3x would equal 3 pi over 4 plus 2 pi k. All right, so x would have to equal pi over, this is crazy, 12 plus, I'm actually going to make this 8 pi k over 4 instead of 2 pi, which would mean that this would be 8 pi k over 12. Okay, and over here I'm going to divide both sides by 3, so this would be 3 pi over 12 plus 8 pi k over 12. So this one here in blue would yield all values that would end up right here, whatever they would be. And it's a formula, right? It's a formula such that we could find all values. K could be a positive or negative number. K is just an integer, right? It's an integer value. So we can simplify this one. Let's say x equals pi over 4 plus 8 and 12 reduce to, oh gosh, what is that, 2 pi k over 3. And this doesn't reduce really any further. I wrote it in terms of a common denominator, but I don't really need to do that unless I'm trying to find specific answers. But there you go. Pi over 12 plus 2 pi over 3 as many times as you want, or pi over 4 plus 2 pi over 3 as many times as you want. There you go, guys. Those are your solutions right here and here. for all possible solutions. Okay, I hope that made sense. We'll see you in part 2. Shoot me a message if you've got any questions. See you next time.